Assalamualaikum. My name is ADLINA with ASRI. My matric number is KA22011. Today, I will briefly explain the first three chapters of our mini project on the production of 2-ethylhexyl or 2-EHA with a target of producing 100,000 metric ton per year. 2-EHA is a liquid chemical used in many industries. It is important in making paint, coating, and plastic. This is because it makes the final product flexible, strong, and resistant to water and weather. The chemical is made through a reaction between acrylic acid and 2-ethylhexanol. This reaction produces 2-EHA and water, but this chemical can be harmful if it not handled carefully, so safety guidelines from agencies like EPA and ECHA must be followed. Our main goal in this product is to design a process that can produce 99.5% pure 2-EHA safely and efficiently. Next, chapter 2 is the thermodynamic model. In this part, we study how the chemical behave during the reaction. The system includes four main components: acrylic acid, 2EH, 2EHA, and water. These chemicals have different properties. Some are polar like water and acrylic acid, and some are not like 2EHA. Because of this, we use a special method called unit hop in S10 Plus. This method helps us better understand to simulate the system. It helps us to predict how the chemical will mix and separate, especially during the heating and distillation. Using this model help our process design more accurate and realistic. Next, chapter 3 is binary thermodynamic analysis. Here, we analyze how pair of chemicals behave together when we heat them. We use the XY diagram, which show boiling and condensation point at different composition. We study four pairs. The first one, water and acrylic acid. Second, water and 2-ethylhexanol. Third, water and 2-EHA. Last, acrylic acid and 2-EHA. In all cases, the diagram shows that no isotope were formed. This means we can use normal distillation to separate them, which make our process simpler and cheaper. Also, the curve shows a good separation between vapor and liquid phase, meaning that the mixture can be separated effectively.
My name is ROWENA and my matrix ID is K22007. I'm going to present regarding the process flow diagram, feed material flow rate, and reactor modeling. For the process flow diagram, pure 2EH and pure AA are mixed and heated to the desired reaction temperature prior to entering the reactor of R1 to 1. The reaction is performed in the presence of homogeneous or heterogeneous acidic catalyst, followed by product recovery and separation by distillation at T101 and T102. The information given in the question are molecular weight of 2-ethylhexyl acrylate, plant operating per year and target plant production, which are set at 100,000 tons per year. In order to achieve the intended production rate of the final product despite losses occurring in the distillation column, the feed amount was intentionally set slightly higher. This strategy helped compensate for purification inefficiencies, allowing the process to still deliver the required quantity of 2-ethylhexyl acrylate. As a result, the feed input in the simulation was modified to ensure steady product recovery throughout the system. For our simulation, rigorous plug flow reactor R plug was chosen as it is resemble the behavior of tubular or magnet reactor used in industry. R plug assumption is perfect concentration and temperature along reactor length. R plug is suitable for high coefficient of purity of 2-ethylhexyl acrylate produced. Based on research done by Santos et al. 2019, the chosen feed ratio is 1 to 3 acrylic acid to 2-ethylhexanol. This indicates that for every 1 mole of acrylic acid, 3 moles of 2-ethylhexanol are fed continuously into the reactor. As shown from the Aspen screenshot above, inlet feed for 2-ethylhexanol is 212.34 kmol per hour, and inlet feed for acrylic acid is 70.78 kmol per hour. Since the esterification process of acrylic acid and 2-ethylhexanol to produce 2-ethylhexyl acrylate is a reversible process, so we got two reactions, which is forward reaction and reverse reaction. Shown here is the kinetic parameter for both forward reactions and reverse reaction. Production of 2-ethylhexyl acrylate obtained in Aspen simulation is 7.8 kmol per hour, meanwhile the conversion of acrylic acid is at 95.84%. The calculated conversion is much more higher than conversion yielded from research done by Santos and al. When they got the conversion in between 68 until 70%. This is due to higher molar feed ratio of acrylic acid to 2-ethylhexanol at 1:3, indicating that 2-ethylhexanol were fed in excess. Excess alcohol shift the equilibrium toward ester formation, increasing conversion beyond equilibrium values. This is supported by literature review done by Mercury et al. 2024 and Lade et al. 2023 that increasing alcohol excess will improve conversion by driving the reversible esterification process forward.
Good morning, my name is VITHYASRI from SELVAM and my matrix ID is K822009. So today I'm going to present about sensitivity analysis of residence time of reactor performance. So within this section, the sensitivity analysis function is employed to examine the influence of residence time and also the influence of temperature on the reaction performance, encompassing conversion, selectivity and yield of the process. In the slide, we can see there's four pictures. Picture number A will be sensitivity analysis setup for molar of alkylic acid enters, and B will be molar of alkylic acid exists, and C will be molar of EHA produced from the reactor, and also D residence time. The first picture is about the formula of conversion of AA, and the next is the formula of 2EHA with respect to AA reacted, which is a selectivity, and the next formula is the formula overall yield of 2EHA per mole of acrylic acid fat. And the next is A, which is about effect residence time on acrylic acid conversion, and the next picture is effect residence time on EHA selectivity, which is B, and the next is the effect residence time on EHA yield. The results are all calculated into conversion, yield and selectivity by using the formulas. Then the results are plotted into graph for better visualizations. The next sensitivity analysis is temperature on reactor performance. All of the data is same as before, which is on residence time, but the graph will be different, which is the first one is AA conversion versus temperature, and the second one is EHA selectivity versus temperature, and the third one is the EHA yield versus temperature. So the table of the calculated values, which consist of acrylic acid conversion, EHA selectivity, and 2-EHA yield, and the unreacted reactants together with undesired product flow rate. So the results are all calculated into conversion, yield and selectivity by using the same formula. Then the result are plotted into graphs for better visualizations.
My name is NURFARISHA and my matric number is K822010. Now I will explain for the separation mentioned in this part in order to achieve an optimal separation efficiency of ethylhexanol and ethylhexyl acrylate. Two different types of distillation model, the STW and Bradford, are used. Initially, we will use shortcut distillation STW for both distillation to achieve the parameter information for reference model. Here at T101 and T102, we use the STW. For T101, water is defined as light key and ethylhexanol is defined as heavy key, which will allow the removal of water in overhead stream, or we call distillate stream, while retaining most of the ethylhexanol and other component in the bottom, since other component that having high boiling point and ethylhexanol as heavy component at the bottom stream. Then the bottom stream will further purified in T102. In this distillation, we set acrylic acid as light key and ethylhexyl acrylate as heavy key. At this part, we remove the residual ethylhexanol in distillate stream, while most of the ethylhexanol will be at the bottom of stream with high purity content. From the data result, the parameter like actual refract ratio, number of actual stage, feed stage, and distillate to feed ratio fraction will be used in refract specification. After we get the data result from the STW, we will proceed to use refract as the parameter need for specification. Both distillation use Kittery boiler, vapor liquid phase, and total condenser. The parameter like actual refract ratio, number of actual stage, feed stage, and distillate to feed ratio fraction is placed as shown in this slide. For the feed stage, will be run up to ensure that the column provide at least the minimum separation need. For the pressure, is adjust to 0.1 to lower boiling point, as making it easy to separate at lower temperature. For the design spec performed for T102 only. So for the first one, used to determine the operating condition required to achieve the desired product specification of 0.995 mass fraction of ethylhexyl acrylate in bottom stream. So the design spec was set using mass purity type with desired target. Selected component as ethylhexyl acrylate and base component are all component. So 2 stream is set as stream of desired design spec. The value is adjusted to distill to feed ratio and the mount is set accordingly. For the next design spec is to achieve the desired product specification of 61.8319 kmol per hour mole flow rate of ethylhexyl acrylate in bottom stream, as it need to meet the annual production rate. Design spec was set using mass flow with the desired target, and other step is the same as before. The value is adjusted with ratio and the bound is set accordingly. So here is the result of separation using reference and after perform the design spec for the water stream, which is at T101, the state stream which is mainly consuming highly water purity. Design spec is not applied in here since it achieved the optimal operating condition 5.8 mole percent, which is the ethylhexanol to water effluent from the plant is less than 10 mole percent. Result from the column achieved ethylhexyl acrylate recovery of 99.99%, which successfully meet the design target of more than 99% recovery as required for the plant production and efficiency.
Assalamualaikum. My name is FADIL and my matrix number is K822013. My part, I will explain process simulations without recycle and with recycles. Firstly, let I start with without recycles. In the setup, alkali acid and ethylhexanol are mixed at a M101 and then to be heated at H101, and then they will go through at the reactor, which are R101s. Here, esterification take place. Then the product will pass through a two distillation column, which are T101 and T102. This will happen separation and purifications. These designs are simple, move straightforward, and then require few controls and monitoring system. Looking at the mass balance, the majority of ethylhexyl acrylate is 12,500 kg per hour is recovered in the main product stream. A small amount, about 1 kg per hour, is lost in the side stream and is labeled as a SY. Combining both give a total output of 12,501 kg per hour. So the mass fraction of ethylhexyl acrylate is 0.999, which means the product purity is 99.99%. From the annual perspective, we produce 105,575 tons per year out of a total of 110,125 tons per year, which is giving us an overall recovery of 99.5%. This shows that even without recycling, the product is highly efficient in a single pass operation. Now, let's move on to the recycle system design. The main reaction and separation step remain the same, which are acid acrylate and ethylhexanol are mixed, heated, and react to form ethylhexyl acrylate and water. The difference here is that the overhead from distillation column T102, which contain and react acid acrylate, ethylhexanol, and water, is sent to the splitter unit, and we as it as a B1. Half of it will purge to prevent build-up of the light component, and the other half is recycled back into the process via pump P101 and remixed with the fresh feed in M101. The additions of the recycle stream offer several key benefits. First, unreacted acid acrylate and ethylhexanol are given another opportunity to react, which increase overall conversions. As the result, the process requires less fresh feed, reducing raw material costs. Also, since only a portion is purged, waste generation is minimized, making the process more environmentally. Additionally, recycling helps to maintain stable flow rates and consistent compositions, which supports a more steady and controlled operations. Now, let's add the result with the recycle stream is placed. The process still produces 110,125 tons per year of ethylhexyl acrylate. From this, 109,575 tons per year is collected as the final product. This gives us the same 99.5 purity, showing that the recycle system maintains product quality. So, although the purity is slightly lower than in the no recycle case, the recycle system brings improvement in conversions, raw material efficiency, and sustainability. To summarize the reason, the non-recycle system is simple and gives very high purity, which is 99.99%. However, it requires more fresh feed and generate more waste. The recycle system, on the other hand, slightly reduce purity to 99.5%, but improve reactor conversions, reduce waste, and lower operating costs. Choosing between the two depends on the production skills, cost priorities, and sustainability goals. That's all from me, and thank you.